In section 5.4, we study exponential functions. The exponential function, f of x equals e to the x, has this graph. If we put in x equals 0, of course e to the 0 is 1, so we get this y-intercept. If x is equal to 1, then f of 1 is equal to e. And if we put in x equals -1, then we get e to the -1, which is 1 over e. Now remember that e is about 2.7, and when you're kind of picturing this in your head, you can approximate 2.7 with around 3 so that you have an idea of where things are. Now looking at the graph, we see that we can plug in all the x values in the negative direction and all the x values in the positive direction, so the domain is -infinity to +infinity. The range, remember that's the y values that result from plugging in the domain. There are no negative y values, and in fact, there's no y value of 0, so the range is just positive numbers from 0 to +infinity. As we look at the graph, the limit as x approaches -infinity of e to the x, we can see it's approaching a y value of 0. And remember that when a limit as x approaches either infinity or -infinity of a function equals a real number, it means that there is a horizontal asymptote at y equals that number, in this case 0. And we can see there's a horizontal asymptote here. Now the limit as x goes to +infinity of e to the x, as x gets bigger, y gets huge, so that is infinity, so there's no asymptote going on the positive side. Some other attributes of the graph of f of x equals e to the x that we notice: over its entire graph, it is increasing. So that's for all x. We can see that it's always concave up for all x. It's continuous for all x. And because it passes the vertical line test and the horizontal line test, we know that it is a one-to-one function. And we know that means that it has an inverse function. If f of x is equal to e to the x, then f inverse of x is equal to natural log of x. So e to the x and natural log of x are inverse functions. So that means they undo each other. If we have e to the x and then we take the natural log of that, that's just going to equal x, because those two functions undo each other. And likewise, if we take e and raise it to a power of natural log of x, those two functions will undo each other, and that's also equal to x. Remember that a function and its inverse undo each other. In this example, we have to give the domain and solve e to the 2x plus 1 is equal to 4. Now, for the domain, we have 2x plus 1 in the exponent of the function, and there are no limiting factors here, so our domain is going to be negative infinity to positive infinity. Now, to solve this, we want to get at that 2x plus 1 that's up in the exponent here. So we have to undo the exponential function. And the way that we undo the exponential function is to take the natural log of both sides. So we will take the natural log of e to the 2x plus 1, which means we have to take the natural log of 4. Now, natural log of the exponential function, they just undo each other because they are inverse functions. So the left-hand side becomes 2x plus 1, and the right-hand side is just the natural log of 4. We subtract 1 from both sides and get 2x is equal to the natural log of 4 minus 1. Now, you have to be careful when you write it this way. This is correct, but many students will make the error of accidentally thinking that this simplifies to become the natural log of 3. So I suggest that you turn it around and write it as negative 1 plus natural log of 4 on that right-hand side. And of course, the left-hand side is still 2x. Now we can divide by 2, and we get that x is equal to negative 1 plus the natural log of 4 divided by 2. And this would be the exact form of the answer. And if we needed to approximate, say, let's approximate to the thousandths place. So go ahead and grab your calculator. Make sure you're comfortable finding this value. We would get that x is approximately equal to, just a quick reminder that you make sure to put this numerator inside a set of parentheses before you divide by 2. And rounding to the thousandths place, which is 3 decimal places, we would get 0.193. And this is the approximate solution. In this example, we have to give the domain and solve the natural log of x plus the natural log of the quantity 2x minus 1 is equal to 0. Now, in considering the domain, we have to look at both of those log functions. So for natural log of x, we will need x to be greater than 0. And for natural log of 2x minus 1, we will need 2x minus 1 to be greater than 0, which means 2x is greater than 1 and x is greater than 1/2. Now, if we put both of these on a number line, this first one of x greater than 0 means we have an open circle at 0 and the arrow going to the right. And for this second one, x greater than 1/2, that means we would have an open circle at 1/2 and the arrow going to the right. So we need both of them true. So that means our domain is going to be from 1/2 to positive infinity. That's where both of these inequalities, x greater than 0 and x greater than half, both of them are true from 1/2 to infinity, and we have to have an open bracket on the half because the half is not included. Now, to solve this equation, before we can use an inverse function, we first have to get a single natural log on the left-hand side. And we know that the log of a plus the log of b is equal to the log of a times b. So the left-hand side becomes the natural log of the quantity x times 2x minus 1. And that is equal to 0. Now, to undo a natural log, we have to take e to the power of that side. So natural log of the quantity x times 2x minus 1 is equal to e to the 0. So we take the exponential function of both sides. Now the exponential function undoes the natural log, and we have x times the quantity 2x minus 1 is equal to 1 on the right-hand side. Distributing, we get 2x squared minus x, and we're going to bring this 1 over to the left-hand side, so it becomes minus 1 equals 0. We can factor this left-hand side into 2x plus 1 times x minus 1 equals 0. Always double check your factoring. 2x times x is 2x squared. A negative 2x plus x gives us a negative x. And 1 times negative 1 gives us negative 1. Now, by the zero product property, we have to take each of the factors in this product and set it to 0. So we have 2x plus 1 is equal to 0, or x minus 1 is equal to 0. Here we will subtract 1 from both sides and then divide by 2. So x is equal to negative 1/2. And here we add 1 to both sides. We get x is equal to 1. Now remember that our solutions must work within our domain. And our domain is from 1/2 to positive infinity. So that means this one won't work. So this one we have to toss out. This is not in our domain of 1/2 to infinity, so we reject it. Then that means our only solution that works is going to be x equals 1. Next, we work with derivatives and integrals involving the exponential function. In its simplest form, the derivative with respect to x of e to the x is e to the x. It's this pretty amazing thing. The function is its own derivative. Then that means that the integral of e to the x dx is going to equal e to the x plus c. Now, if we differentiate using the chain rule, we would have something like d by dx of e to the u. Then that's going to be e to the u times u prime. And this, of course, is the chain rule piece. If we integrate with substitution, where u is equal to g of x and du is equal to g prime of x dx, and we have the integral of e to the u du, then that's going to be e to the u plus c. So let's try some examples and see how this works. In this example, we have to take the derivative with respect to x of the quantity x squared e to the 2x. Now, right away, hopefully you notice that you are going to have to use the product rule because we have an f times a g. So we will do f prime g plus f g prime. F prime is going to be 2x times g, which is e to the 2x, plus f, which is x squared, times g prime, and here we're going to be differentiating with the chain rule. So remember, the derivative with respect to x of e to the u is e to the u times u prime. So this is going to be e to the 2x, and then the chain rule says that we have to multiply times 2 because the derivative of 2x is 2. Now this will simplify to be 2x e to the 2x plus 2x squared e to the 2x. We can factor out a 2 and an x and an e to the 2x, and then we would take that times 1 plus x. In this example, we have to integrate e to the negative x over 2 dx. If we let u equal negative x over 2, then du is going to equal negative 1/2 dx. So working with our integral in the x variable, we have the integral e to the negative x over 2. Now I'm going to leave some space here because looking at my du, I see I'm going to need to put in a negative 1/2 there. And then I'll write the dx. So far, we just have e to the negative x over 2 and the dx from the original integral. Now, because our du needs that negative 1/2, we're going to multiply by 1 in the form of negative 1/2 times negative 2. Make sure you understand that negative 2 times negative 1/2 is equal to positive 1. So all we've really done is multiply by 1. Now we are ready to substitute to the u variable. Out front, we have that negative 2, and that will remain out there. Then we have the integral. We have e to the negative x over 2, which is going to be replaced with e to the u. And then this entire quantity here, negative 1/2 times dx, we see can be replaced with du. Now here, this becomes negative 2. Now the integral of e to the u du is equal to e to the u plus a constant. Because this is an indefinite integral, we have to go back to our x. So this becomes negative 2e to the negative x over 2 plus c. In this example, we have to integrate e to the tangent of x over cosine squared of x dx. Now, if you're not sure what you should let the u function equal, a good place to start is the inside of a composite function. E to the tangent of x is a composite function, so let's try letting u equal tangent of x. Then du is going to equal secant squared of x dx, or we could say that du is equal to dx over cosine squared of x. These two expressions are equivalent to each other. All we need to do is reorganize our integral a little bit. We have integral of e to the tangent x times dx over cosine squared of x. So all we did was reorganize. The e to the tangent of x is still there, the dx is still there, and the cosine squared of x is still there in the denominator. Now we can do the substitution into the u variable, and we have e to the tangent of x is going to become e to the u, and the dx over cosine squared of x, that gets replaced with du. We know that the integral of e to the u du is e to the u plus c. Because this is an indefinite integral, we have to go back to our x. So now this becomes equal to e to the tangent of x plus c. Here we have to integrate e to the 4 over x squared dx. So if we use this strategy where we let u be the inside of a composite function, then u would equal 4 over x, which is 4x to the negative 1. Then du is going to equal negative 4x to the negative 2 dx. Or we could write du as negative 4 over x squared dx. Now, if we organize our integral in the x variable a little bit, we have the integral e to the 4 over x. We have that x squared in the denominator, and we have our dx. And we see that we are missing this constant of negative 4 that we need for du. So if we multiply by 1 in the form of negative 4 times negative 1/4, we're only multiplying by 1, and we haven't changed our expression at all. Now we are ready to substitute to the u variable. So we have that negative 1/4 out front that has to come down. We got the integral. This e to the 4 over x gets replaced with e to the u, and then this entire negative 4 over x squared times dx gets replaced with du. And remember, you can only do that replacement if you have an equation that allows you to do that. We have an equation here that says du is exactly equal to negative 4 over x squared dx. That's why we are able to make that replacement. So this becomes negative 1/4 e to the u plus c. And because this is an indefinite integral, we have to go back to our x. So this becomes equal to negative 1/4 e to the 4 over x plus c. In this example, we have the integral from 0 to radical 2 of x e to the negative x squared over 2 dx. The most likely candidate for our u variable is the inside of this composite function. So let's let u equal negative x squared over 2. Then du is going to equal negative 2x over 2 dx, which simplifies to be du equals negative x dx. So let's reorganize a little bit. We've got the integral from 0 to radical 2. I'm going to write the e to the negative x squared over 2 first, because I see that I need that x, that's right here, over here with the dx. So we're going to need to get in a constant there, and then we have x and dx. So far, all we've done is move things around. We put the e to the negative x squared over 2 first, followed by the x and the dx. Now we see that for our du, we need negative x dx, so we're going to multiply by negative 1 on the inside and by negative 1 on the outside. Now we are ready to do our substitutions. So this is going to equal, we have that negative sign out front that stays there. Then we have to integrate, and now we have the lower limit and the upper limit that have to be converted over to the u variable. So let's come off to the side here. When x is equal to 0, we plug 0 in for x, and u would be negative 0 squared over 2, which is equal to 0. So the lower limit is still going to be 0. Then the upper limit was radical 2, and so we have to do negative radical 2 squared over 2, and that is going to equal negative 1, because radical 2 squared is 2, and negative 2 over 2 is negative 1. So that upper limit is now negative 1. Here, the e to the negative x squared over 2 is going to become e to the u. And then finally, the negative x dx is going to get replaced with du. Now, one thing I can do to simplify is I can get rid of this negative sign right here if I just switch the limits of integration. So this becomes the integral from -1 to 0 of e to the u du. And all we did was apply the rule that said the integral from b to a of f of x dx is equal to the opposite of the integral from a to b of f of x dx. And anytime I can get rid of a negative sign, I really like to do that. So now we know the integral of e to the u du is going to be e to the u, but this time we don't have a plus c because it's a definite integral that we are evaluating from -1 to 0. And just a quick reminder that since this is a definite integral, we definitely never go back to our x. We are going to plug in these values in the u variable. So this is equal to e to the 0 minus e to the -1, which is 1 minus 1 over e, which if I get a common denominator is equal to e minus 1 over e. In this example, we have to find the relative extrema of f of x equals x squared e to the x. Now we know to find relative extrema, we need the derivative, and hopefully you notice that you are going to need to use the product rule to find this derivative. So f prime of x, if we take the derivative of the first, we get 2x times the second e to the x plus the first x squared times the derivative of the second e to the x. We can factor out an x e to the x, and we have left 2 plus x. Now, in order to find the relative extrema, we need to find the critical numbers. So we are going to set this equal to 0 or does not exist. And this expression has three factors: a factor of x, a factor of e to the x, and a factor of 2 plus x. This first factor will equal 0 whenever x is equal to 0. We know that e to the x is greater than 0 for all x, so that's never going to equal 0. And 2 plus x will equal 0 when x is equal to -2. As far as does not exist, x exists everywhere, e to the x exists everywhere, and 2 plus x exists everywhere, so this is a never. Let's make our sign graph. We know that f prime is equal to 0 at -2, and it's equal to 0 at 0. Now if we pick some test points, for example -3, then we would have a negative here. This one's always positive, that's what this tells us. And we would have a negative here. So a negative times a negative is a positive. A test point here would be -1. We would have a negative times a positive is a negative. And a test point here would be 1. Positive times positive is a positive. By the first derivative test, if the first derivative changes from positive to negative, we know that happens at a max. And if it changes from negative to positive, we know that happens at a min. So that means we will have a relative max at -2. We will need to figure out f of -2. So f of -2 is equal to -2 squared times e to the -2, which is 4 over e squared. So that's the y value here. And then we have a relative min at 0. Pretty easy to see f of 0 is going to equal 0. In this example, we have to find the equation of the tangent line at the point 1, 1. We are given this equation, 1 plus natural log of the quantity xy is equal to e to the x minus y. Now, to find the equation of the tangent line, we know that we need a point, which we have, and a slope. And the slope of the tangent comes from the derivative, so that's going to be dy dx, and we will need to evaluate that at the point 1, 1. So to get to dy dx, that tells us we need to take d by dx of both sides of this equation. So if we take the derivative with respect to x of the left-hand side, then we take the derivative with respect to x of the right-hand side. Now what I want you to do right now is pause the video and see if you can write out the next line and then restart when you're ready to check your work. The derivative of 1 is 0. Remember that the derivative with respect to x of the natural log of u is equal to u prime over u, or you can write it as 1 over u times u prime. I think I will do it this second way this time. So the derivative of natural log of the quantity xy would be 1 over xy. That's the 1 over u part. And then to find u prime, because this is a product, we have to use the product rule. So we do the derivative of the first, so the derivative of x is 1, times the second, y, plus the first, x, times the derivative of the second, which would be 1 dy dx. And that has to equal the derivative of the right-hand side. And be reminded that the derivative with respect to x of e to the u is equal to e to the u times u prime, the chain rule piece. So the derivative with respect to x of e to the stuff is going to be e to the stuff times the derivative of the stuff. So the derivative with respect to x of x is 1 minus the derivative with respect to x of y is 1 times dy dx. Now we know that ultimately our goal is to solve for dy dx, so we need to simplify so that we can gather up the dy dx terms. Over here on the left-hand side, we have to distribute this 1 over xy, and 1 over xy times y would be 1 over x, plus we have 1 over xy times x dy dx is going to be 1 over y dy dx. On the right-hand side, we have to distribute this e to the x minus y. So we take that times 1, we get e to the x minus y, and then we take it times a minus dy dx, so we subtract e to the x minus y dy dx. So now we will gather any term that has a dy dx over on the left-hand side, and any term that does not have a dy dx, these two, will be on the right-hand side. So this term is going to stay on the left. We have 1 over y dy dx. This term has a dy dx, so we will bring it over to the left-hand side, and it becomes plus e to the x minus y dy dx equals this term, e to the x minus y, stays put on the right-hand side, and then this 1 over x will need to come over to the right-hand side and be subtracted. Now on the left-hand side, we can factor out dy dx, and we would have left 1 over y plus e to the x minus y. The right-hand side stays exactly the same as it is, e to the x minus y minus 1 over x. Continuing to simplify, we will keep the dy dx on the left-hand side, and the right-hand side becomes a big rational expression. The numerator is going to be e to the x minus y minus 1 over x, and the denominator is going to be 1 over y plus e to the x minus y. Let's simplify. Dy dx is equal to clear out the complex fraction, we multiply by 1 in the form of the LCD over itself. So that's going to be xy over xy because of these extra denominators that we have. So distributing the xy times the first term, we get xy times e to the x minus y minus xy times 1 over x becomes y. In the denominator, when we distribute, we have xy times 1 over y becomes x plus xy times e to the x minus y. Nothing cancels there. So now we need to find the slope of our tangent line. And remember, we said that the slope of the tangent was going to be equal to dy dx evaluated at the point 1, 1. So now let's do this calculation. So this x becomes a 1, this y becomes a 1, and then we have times e to the 1 minus 1, which would be 0, minus y, which is 1. In the denominator, x gets replaced with 1 plus x times y is 1 times 1. E to the x minus y is 1 minus 1 in the exponent, which is 0. So this is e to the 0. So in the numerator, we know e to the 0 is 1. So this first term is 1, and we have to subtract 1. In the denominator, we're going to get 1 plus 1. So this is 0 over 2, which is equal to 0. So our slope is 0. This is going to be a horizontal tangent. So now we know the slope of our tangent line is equal to 0. We know our point is 1, 1. So that means the equation of our tangent line is just y equals 1. The equation of a horizontal line always looks in this form. Y equals whatever the y value is.